If you're asked to verify that two functions are inverses of one another, that is, algebraically they do the opposite operations in the opposite order, algebraically what you're supposed to do is calculate or find the composition of your functions given in both directions. For example, f circle g and also g circle f. When the compositions are done both ways, if both of them come out with an answer of x, then you have algebraically verified that these two functions are inverses. Okay, so let's look at the top composition, f composed of g. That is f with g subbed in, so that's f of 5x plus 4. We go to function f, replace its variable with 5x plus 4. So that gives us 5x plus 4. That's where the variable went, but we put the other function in it. Minus 4 all over 5. Okay, so that is function f with function g subbed into it. In the numerator, we have 5x plus 4 minus 4. Well, the 4's cancel one another, and that leaves us 5x over 5. Well, the 5's cancel each other, leaving x. Okay, now that's a good start. If any one of these compositions does not come back out to x, you don't even have to do the other one. We do have to make sure that both do come out to x, but if either one of them or both of them do not come out to x, then you don't have to go any farther. They're not inverses. Okay, so on the next composition, g is going to take on function f. Function f is x minus 4 over 5. X minus 4 over 5. Well, g is 5x plus 4, so that's 5. The variable takes the other function, so we have x minus 4 over 5, where the x used to be, plus 4. Our 5's cancel, and that leaves us x minus 4 plus 4. And what happens there? You bet. We just get an x. If both compositions come out to x, then we can say f and g are inverses. Of one another. Let's look at two different functions and also verify algebraically that these are inverses of one another. I also want to extend this into how you look at domain for a function and its inverse, because you may have a restricted domain for one function and an unrestricted domain for the other, but those will have to go hand in hand. So let's go first and verify that our compositions, both directions give us x. So we're going to do f composed of g. Okay, so function f is square root of x plus 2. So that is square root x plus 2. Now the x is going to receive the x squared minus 2. X squared minus 2 plus 2. Okay, so that is square root x squared minus 2 plus 2. The 2's cancel. And square root of x squared is x. Alright, so that's a good start. Let's check the other composition in the reverse direction. G composed of F. Okay, so G is going to receive F, x squared minus 2, but the variable is traded out for function F, so that's square root of x plus 2 squared minus 2. A square and a square root, they undo one another, so that's x plus 2 minus 2, and that comes out to x. Okay, so we have just verified algebraically that F and G are inverses. Okay, now let's look at function F on a graph. Feel free to use your graphing calculators. If you graph the square root of x plus 2, you will get a graph that starts at the point -2, 0 and hooks upward and over like this. That is the graph of f of x. And take a moment to check that with your graphing calculator. Go to y equals, type in square root of x plus 2, make sure that all of it is under the radical, hit graph. Okay, so function f has a domain of -2 to infinity. These are all the values of x that show up on the graph. The range, the lowest y value is 0, and as it goes right, it gradually goes up, so all positive y's are covered. Now, there's a special phenomenon that happens when you graph, let me do this in green. When you graph functions that are inverses of one another, they are symmetrical about the line y equals x. It's a diagonal. Inverse graphs are symmetrical about this diagonal. So if the original graph of f of x starts at -2, 0 and has its up and over orientation, its inverse, which just happens to be g, is going to start at 0, -2. Every point on f, if you reverse the order and replot, then you will get the graph of g. And they make a very beautiful mirror image of one another across that y equals x diagonal. Now the catch is, your domain and range will be inverted as well. The domain of g will be equal to the range of f. And if you notice, the red graph starts at x equals 0, and as it goes right, it goes up, but it continues to go right, covering all positive x's. The domain of f will have to become the range of g. Notice on the red graph, your lowest y value is -2, but as it goes up, it covers all the positive y's. And so inverse graphs are beautifully symmetric about one another. I do want to point out that if you were to graph g all by itself, it would actually be this parabola. But if you draw it in its entirety, the graph in red will not pass a horizontal line test. so you have to take it off. G is best defined this way. X squared minus 2, but only allowing x to be 0 or larger. Okay, in this slide, we're going to look at, if you're given a graph, how to visually determine, one, whether it's a function, and B, if it's a one-to-one function. If it's a function and it's one-to-one, then it will have an inverse function as well. In the top graph, this one is not a function because it fails the vertical line test. If a single vertical line can strike your graph more than once, then that graph is not even a function. Not a function. Suppose that a vertical line does only strike your graph one time, then it's a function because each y value only has one x. But just because it's a function doesn't mean that it's one-to-one, where every x has only one y. So it's not one-to-one. If it's not one-to-one, it has no inverse function. And then finally, our last graph is a function. A vertical line only strikes it once. And so that's how you compare different types of functions, whether they have an inverse or not, and whether they're even functions or not. Not all of them are functions. If you're given a function and asked to find its inverse, then you follow a four-step procedure that if you verify, for example, you're going to want to graph 2x plus 3 on your calculator and just visually verify that it's a line which will pass both vertical and horizontal line test. And this graph does. So if you know you have a one-to-one function, it will have an inverse that's also a function. First step is change your function notation to the letter y. Second step, switch places with your x and your y. Third step, solve for y. Subtract 3, divide by 2, and then your last step is to replace y with the inverse notation. F inverse of x is equal to x minus 3 all over 2. Let's try to find the inverse of x squared minus 4. Now we're going to have to restrict the domain to 0 or any value larger, because if you were to graph x squared minus 4 in its entirety, you would get a parabola that hits the x-axis, hits the y-axis down at -4. And that's not a problem as far as being a function, because that graph will pass a vertical line test. Where the issue comes up is if you don't restrict your domain, it won't pass a horizontal line test. And if it doesn't pass a horizontal line test, then it's not one-to-one, and that means its inverse will not be a function. So that's why we shave off the left side of it. Now that part of the graph will pass both vertical and horizontal line test, and so that part of it is a one-to-one function. And I just wanted to explain why we have to restrict the domain. Okay, going through our four-step process, step 1 is change f of x to y. And so that's going to give us y equals x squared minus 4. Step 2, change places with your x and y. Just swap them out. Step 3, re-isolate the y. So we're going to add 4. And use the square root property. Take the square root of both sides. And that gives us y equals the positive and negative square root of x plus 4. Now we have to make a decision here. Since the x's were forced to be positive in the original problem, we're going to use the positive root in the inverse. Positive x's in the original problem, positive in the inverse. And then step 4 is just change your y to the inverse notation using the positive square root of x plus 4. If you were to add that graph into the one towards the top of the screen, this one is f. If you were to also graph square root of x plus 4, it starts at negative 4, 0, while our other one, the original, started at 0, negative 4. They're always balanced out that way. The domain of the original will be the range of the inverse. The range of the original will be the domain of the inverse. They always work opposite. And so that would be the graph of your f inverse. Notice how there's a beautiful line of symmetry through that diagonal. They will always have that.